Hello, welcome to the 747-400 PC Systems Review. Our video today will cover the aircraft systems, unaligned numbers, and immediate action items for the 747-400. As always, refer to your flight manual and flight operations manual for current information. Our review today will start in the upper left-hand corner of the overhead panel with our electronic engine controls. Each EEC has two modes of operation. There's a normal and an alternate mode. With the EEC in normal, EPRs are controlling parameter for setting thrust. The normal mode will provide overboost and overspeed protection for both the N1 and N2 compressors. The alternate mode, N1 is the controlling parameter. There is no overboost protection, however you do retain the overspeed for both the N1 and N2. The EECs are normally operated with them in the normal mode. However, during reverse thrust after landing, the EECs will automatically cycle into the alternate mode. While you're in reverse thrust, you do not have overboost protection, but you do retain the overspeed protection. If you were to look up here during reverse thrust, the EECs would show you in normal, however you are actually in the alternate. You can be dispatched with an EEC in-op in the normal mode. The irregular procedure has us placing all of these EEC switches in alternate. If any EEC for any reason is in the alternate mode, the auto throttles will not engage. Below the EEC control panel is your IRS control panel for your IRSs. Three IRSs, a left, a center, and a right. The normal power source to IRSs is AC power, and the gauge for left, center, right is 312, thus AC bus 3, AC bus 1, and AC bus 2 as the primary power source. The backup power source to all three IRSs is the APU hot battery bus. If the center IRS was to lose AC bus 1, it would go to the APU hot battery bus and run for 5 minutes and then shut down. If the left or the right IRS was to lose its respective AC bus, it independently can also go to the APU hot battery bus and will run for at least 30 minutes, depending on the availability of your service bus. If your service bus is available, the battery chargers will actually run these two IRSs indefinitely. If the service bus is not available, the APU hot battery bus is actually draining the battery, thus the 30 minutes. During an external walk around, you can tell if an IRS is switched over to the APU hot battery bus by the continuous horn from the nose wheel well. IRSs do not navigate. The FMCs, left and right, are responsible for navigation. The IRS provides input to the FMCs for that purpose. To go from off to nav, a full-up alignment takes approximately 10 minutes, provided position is loaded. With a fully aligned IRS in the nav mode, it will generate 4 items on your PFD. The IRS will generate the attitude picture, the IRS heading. The accelerometer portions of your IRS will give you vertical speed and the green airspeed trend arrow. The attitude position of the IRS will shut down the accelerometer portions. As a result, the vertical speed and airspeed trend on your PFD will be lost. However, the attitude mode of an IRS will retain the attitude picture and the IRS heading. The heading will have to be updated occasionally through the CDU page, position page 2. Moving down and below the IRS control panel is your electrical control panel. Several switches on this panel. We'll start with the utility switches left and right. Attached to each AC bus are 2 additional buses called galley and utility. They're attached to that respective AC bus through load controllers. If an AC bus is overloaded, it will start load shedding the galleys first, and if the power requirement is even greater, it will then shed the utility, repowering in reverse order. If a load shed occurs, the off lights will not illuminate in the respective switch. Turning a utility switch left or right off will kill both galleys and both utilities on the respective side. It will not kill the respective AC bus. Below the utility switches is your battery switch. The battery switch controls both the main and APU batteries, which are guaranteed to last 30 minutes. Upper right-hand corner of your electrical control panel is your APU control switch. The APU can be started on the ground. It cannot be started in flight. However, you can take it in the air running. If you take off with the APU running, the APU can give you bleed air up to 15,000 feet. The APU is allowed to run to 20,000 feet as long as you're not in icing conditions. The APU cannot give you electrical power in the air. The battery switch must be on to start and operate the APU, regardless of how your airplane is powered. If your airplane is fully powered and the battery switch is off, the APU cannot start. And if it is running, it will shut down. All right, so talk about the electrical system. Electrical system, AC and DC power. Captain's instruments, normally powered by captain's transfer bus. Captain's transfer bus provides the captains with his instrumentation power. Captain's transfer bus, normally powered by AC bus 3. AC bus 3 is powered, it will power your captain's transfer bus. Captain's transfer bus is also backed up by AC 1 as the alternate source. First officer's instrumentation. First officer's instruments receive power from first officer's transfer bus. First officer's transfer bus normally powered by AC bus 2. Backed up, again, by AC bus 1. So bus 1 is the backup power source for both your captain and first officer's transfer bus. Real critical flight instruments, things that the captain needs to fly in instrument conditions, are going to come off your standby power system. Standby power is two separate buses. APU standby bus and the main standby bus. Both the APU standby and main standby buses are controlled through the standby power switch. APU standby power is normally powered by the captain's transfer bus. If the captain's transfer bus is powered, it will power the APU standby, regardless of the source, whether it be AC bus 3 or AC bus 1. As long as it's powered, it'll power your APU standby. Main standby bus is normally powered by AC bus 3. As long as the normal power source is AC bus 3 and captain's transfer available, your two standby buses remain powered. However, if failures occur, the standby power system is going to be backed up by hot battery bus through an inverter to the respective hot battery bus. APU standby is off the APU hot battery bus. The main standby is off the main hot battery bus. They go through the battery switch. In this case, the battery switch is closed. This will drain the batteries if your service bus is not powered. Service bus. Service bus is up here off of AC bus 1. If AC bus 1 is powered, it will power your service bus. That's your normal power source. The service bus gives us our two chargers. If the service bus is powered, your battery chargers are running, which are actually physically powering your hot battery buses and in turn powering your standby power system. In order for this power to occur, the battery switch must be closed. That's the AC side. The DC side, you have your battery buses, main battery bus and APU battery bus. Your two battery buses are normally powered by DC bus 3. DC bus 3 is normally powered through the TR from AC bus 3. If DC bus 3 is powered, it will power the two battery buses, regardless of the battery switch position. AC bus 3 is your normal power source to DC bus 3. Also remember that the DC tie bus can power DC bus 3. In any event, if DC bus 3 was to lose power, your hot battery buses, in this case the main hot battery bus is the backup power source to the main battery bus. The APU hot battery bus is the backup power source to the APU battery bus. Again, in order for this transfer to occur, the battery switch must be closed. If everything was normal, the standby power switch was an automatic. Captain's transfer powers the APU standby. AC bus 3 powers the main standby. Captain would have all of his instrumentation. AC bus 2 would power the first officer. First officer would have all of his instrumentation. The battery buses are powered by DC bus 3. In the unlikely event the battery switch was to wind up in the off position for some reason, this would not affect the system. However, if a failure was to occur, such as losing the captain's transfer, APU standby would go looking for the APU hot battery bus, but with the battery switch open, the transfer cannot occur. Likewise, if the main standby was to lose AC bus 3, it would go looking for the main hot battery bus, the transfer could not occur. So, normal operations, we keep the battery switch closed. Continuing our discussion with the electrical panel and the overhead, standby power switch again controls both the APU and the main standby buses. If the airplane was fully powered with the standby power switch in auto, moving the standby power selector to off will kill both the APU and main standby buses. As a result, the captain would lose his critical items such as the PFD, the ND, the left FMC, left CDU, and so forth. The only time operations ever turns that selector in the off position is during the securing the airplane checklist. All other times, the standby power selector should be in auto. If the standby power selector is moved to battery, that forces both the main and APU standby buses to their backup power source. This will drain the batteries. Even though AC bus 1 may still be powered, the battery chargers are shut off by taking the standby power selector to battery. During the cockpit setup, the captain is required to pre-flight the standby power system. By moving the standby power selector from auto to battery, this will force both standby buses to their hot battery buses, turning off both battery chargers. To ensure that the system works, the captain will check the PFD remains powered, the ND remains powered, the primary ICAS remains powered, and the left CDU remains powered. To ensure that the system has switched over to the backup power source, it's important to check the 2 battery discharge messages on the primary ICAS. It will then position the switch back to automatic, again making sure that the captain's PFD, ND, primary ICAS, and left CDU remain powered, and most importantly that your 2 battery discharge messages go away on the primary ICAS. Continuing with the electrical panel, in addition to your AC buses we see depicted here, there are 2 additional buses I'd like to think of here on your electrical panel. One of them physically placed here in relation to your system, the other one physically placed here in relation to your system. The bus up here to the left of external power 1 would be the ground handling bus. The ground handling bus provides power to such items such as the cargo loading, to include the doors, the lights, the rollers, fueling, except for your stabilizer, and the aux hydraulic pump in System 4. The primary power source to that ground handling bus is external power number 1, backed up by APU generator number 1. Powering the ground handling bus requires the avail light or the on light in either of these 2 switches. External power needs to be plugged in. It does not need to be on. If you place external power on, it will still power the ground handling bus. If external power number 1 is not available, start your APU. As soon as the avail light comes on, the ground handling bus will be powered. You can place the generator online, powering your airplane. It will still power the ground handling bus. If there is no light in this switch or this switch, regardless of the other status of your airplane, the ground handling bus is not powered. It is impossible to power the ground handling bus from external power number 2 or APU generator number 2. The bus in this location here, the service bus is what Doc calls it. It's called the ground service bus. However, the ground handling bus only works on the ground. The service bus works anytime AC bus 1 is powered, such as in flight. So to help you distinguish between the ground handling bus and the ground service bus, I dropped the word ground from here. So on your service bus, the important item to you on the service bus are your 2 battery chargers. Also your stab fueling, and a number 2 aft boost pump for APU operation on the ground. The service bus, again, is normally powered by AC bus 1. Anytime AC bus 1 is powered, it will power your service bus, whether you want it or not. Additionally, your service bus can be powered from your ground handling bus through the switch at the flight attendant's position, door 2 left. When pushing that switch, that would take the supply to your ground handling and send it to the service bus directly, bypassing your airplane. That will not power AC bus 1. AC bus 1 can power your service bus, not the other way around. Split system breaker, not depicted here on this schematic, but on your synoptic. The only power source you can parallel across a split system breaker is an engine generator. No other power sources can be paralleled across. It's impossible to synchronize them. Bus tie switches, auto and isolated. The airplane has the ability to isolate an AC or a DC bus and tell you about it on a primary ICAS. However, if you physically reach up and isolate a bus tie, you are opening both the AC and the DC buses. During a LAN 3 situation, the airplane will automatically isolate AC bus 3, AC bus 1, and AC bus 2 for the left, the center, and the right autopilot sterile sources. During that time, the panel will show auto, although the bus ties are truly isolated. The AC and DC tie buses will remain powered at that time through generator 4 in case generator 4 has to step in and pick up a faulty generator. Generator control switches. During the cockpit setup, your captain's going to turn the generator control switches on, but they will still stay off because the generators are not physically turning. It's impossible for the relay to close. IDG disconnects. If you disconnect an IDG, maintenance has to reconnect it on the ground with the engine shut down. There's an amber drive light in each IDG. The amber drive light illuminates for IDG high oil temperature or IDG low oil pressure. Dropping down below the electrical panel is your hydraulic control panel. Hydraulic control panel, there are 4 separate totally independent hydraulic systems referred to as system 1, 2, 3, and 4. Each system has 2 pumps which can pressurize it, an air demand pump and an engine-driven pump. Air demand pump referred to as ADPs, engine-driven pump referred to as EDPs. Air demand pumps take pneumatic air from your pneumatic system to operate. Air demand pumps are 3-position switches, off, auto, and on. With the ADP in the off position, the air demand pump is not allowed to run regardless of what's going on in your hydraulic system. With the ADP in the on position, that air demand pump will run continuously as long as it gets pneumatic air, again, regardless of what's going on in your hydraulic system. With the air demand pump switch in the auto position, there are 2 things which will activate the respective air demand pump in auto. Low system pressure, be it EDP failure or high demand, or taking the respective fuel lever to cut off, will automatically activate the respective air demand pump. In addition, on 1 and 4, in addition to low system pressure and taking a fuel lever to cut off, trailing edge flap operation will cause those pumps to operate. If you're on the ground while the trailing edge flaps are in transit, air demand pumps 1 and 4 will physically run. Once the flaps stop, the air demand pumps will shut down. In flight, air demand pumps 1 and 4 run continuously until the trailing edge flaps are up. The aux pump in System 4, again, is the electrically driven hydraulic pump to allow maintenance to build pressure in your system to tow the airplane. That aux pump is powered by the ground handling bus. EDPs for each engine is engine-driven pump. If the engine is turning, the pump will be turning unless it seizes. For this discussion, we'll assume that the engine is turning. We're flying along at 30,000 feet doing 8.5 Mach. With the switch on and the pressure light out, the EDP is turning. It is putting out system pressure, and as a result, it is getting lubrication for cooling. If I was to reach up and turn the switch off, the on light would go out, the pressure light would illuminate. The EDP is still turning. It is not putting out system pressure, but it is getting lubrication for cooling. If we pull the fire switch for that engine, that will shut off the fluid supply to the EDP and not the ADP. As a result, the hydraulic system will still operate. The air demand pump takes pneumatic air from another point of your airplane, not the engine. We'll pressurize the system. The fluid supply is shut off to the EDP. As a result, the pump is not putting out pressure, and it is no longer getting lubrication for cooling. However, if the engine is windmilling, the EDP is still turning. Some more chalk talk with regards to the hydraulic power system. Hydraulic power, if we balance things out, it's a little easier to recall what comes off of what hydraulic system. Again, we have the four systems, 1, 2, 3, and 4. There's two items common to all four systems. All four systems operate some type of flight control. All of your flight controls on this airplane are hydraulically powered. Majority of them are dual sources, so a single hydraulic system failure is probably not going to affect that many flight controls. In addition to flight controls, thrust reversers on their respective system. So all four systems have flight controls and thrust reversers. 1 and 4. 1 and 4 are your big systems, things you need for takeoff and landing on hydraulic systems 1 and 4. Items such as gear, trailing edge flaps, and brakes. Likewise, System 1 has gear, trailing edge flaps, and brakes. So flight controls, thrust reversers, gear, trailing edge flaps, and brakes. Specifically, inboard items, inboard are on System 1. System 1, Roman numeral 1, English letter I. Outboard systems must be on 4. Inboard gear, that would be the nose and body gear. And you're talking the normal extension, retraction, and steering for both your nose and body gear. Inboard trailing edge flaps, and alternate brake system. Outboard gear, that's called the wing gear, outboard trailing edge flaps, and normal brake system. Items that are common. Everything in life always has an exception, so it applies here. System 1 has an autopilot servo, in this case specifically the center. System 4 does not have an autopilot. That's the commonality between 1 and 4. 2 and 3. 2 and 3. In addition to flight controls, thrust reversers, we have stab trim. Stab trim is a flight control. We could put that up here under flight control, but we like to specifically point out that half of your operation comes off at System 2, the other one off at 3. Half of something else is your elevator fuel computer. Elevator fuel resistance comes from that computer, which takes hydraulic input from System 2 and System 3. Each system has a yaw damper. Each rudder has a yaw damper. One of them is pressurized by System 2, the other one by System 3. Autopilot servos. The left autopilot servo is on System 3. The right autopilot servo is on System 2. These are items that are common. The only difference between 2 and 3, 2 has alternate brakes. There is no brake source on System 3. All right, let's discuss the brake systems. Normal brakes are on System 4. Everything being normal System 4 pressurized, brakes are available on System 4. If System 4 was to fail, the brake system would automatically move over to the alternate brakes on System 1. If System 1 was to fail, the brakes would automatically move over to alternate brakes on System 2. If that fails, the brakes will then move back to the accumulator in normal System 4. Normal brakes has anti-skid, very elaborate individual wheel anti-skid system. It also has auto brakes. The alternate brake system has anti-skid. It's not as elaborate, it's paired up in axles. It does not have auto brakes. Alternate brake system is identical to this brake system. The only difference between these two systems is which system pressurizes it. This system is entirely different than the normal brake system on System 4. Further discussion on your brake system with reference to your hydraulic control panel on the overhead panel, your normal brake accumulator, and your brake source light. We'll simulate that all 4 hydraulic systems are depressurized, and as a result, the brake source light will be illuminated. Your brake accumulator indicates pre-charge pressure. The underlying number here is 750. We'll indicate we'll show that indicates 750. Brake source light is illuminated, and I reach up and pressurize System 2 hydraulics with the air demand pump. System 2 is pressurized. That will not bring up the brake accumulator gauge. The brake accumulator gauge is in System 4. System 2 pressurizes the alternate brakes. As a result, it cannot bring the gauge up. The brake source light is out, though, indicating that brakes are available on hydraulic System 2. I then reach up and pressurize hydraulic System 1. System 1 is pressurized. Again, that will not bring up the brake accumulator gauge. The brake source light is still out, indicating the brakes have gone from 2 over to 1. I then reach up and pressurize hydraulic system number 4. System 4 is pressurized. That will bring the pre-charge up to system pressure, should be approximately 3,000 psi. The brake source light is out, indicating the brakes have gone from 1 over to 4. So what we've done here is I've gone in reverse order of priority. System 2 started it out, could not bring up the gauge. Pressurized 1, 1 took it from 2, again cannot bring up the gauge. Pressurized 4, 4 takes it from 1 and brings the gauge up. Now if I was to then reach up and kill System 4, I lose system pressure in 4, the brake should go to alternate System 1. But my brake source light illuminates, indicating that change did not occur. So as a result, my brakes are right here on the accumulator, which is not going to stop the plane. The accumulator is designed to set and hold the parking brake only. One last discussion on the hydraulic control panel are your indication lights. SIS fault lights for each hydraulic system. The SIS fault light will illuminate for low reservoir quantity, high system temperature, or low system pressure. Amber pressure lights for the respective air demand pump will illuminate anytime the air demand pump is commanded to run and is putting out low pressure. In addition, low EDP pressure lights whenever the EDP output pressure is low. Remember, you have to lose both an ADP and an EDP to cause the SIS fault light to come on for low system pressure. Captain, prior to pushback, will pressurize System 4 using the aux pump. The SIS fault light will go out because the system is pressurized with the aux pump. The ADP and EDP low pressure lights will remain illuminated. It will then pressurize System 1 using the air demand pump. As a result, the amber low pressure light for the air demand pump will go out, thus pressurizing the system, putting out the SIS fault light. The reason we're pressurizing System 4 for the pushback is for primary brakes in a normal brake system. The reason we're pressurizing System 1 for the pushback is for body gear steering with a backup benefit of backing up the brakes. Our discussion now will move to the aft right corner of the center aisle stand with our auto brakes. Auto brakes, we can use this system for takeoff by selecting RTO. RTO is selected during the cockpit setup by the captain. RTO is armed whenever the ground speed is greater than 85 knots. RTO is activated by closing the throttles. You will get max braking to a complete stop if you do not disarm RTO. RTO will not factor in reverse thrust. RTO does not compute an acceleration rate. It allows max braking to occur to a complete stop. You cannot physically outbrake RTO. If RTO is no longer desired and you wish to disarm it, the preferred method is to touch the brake pedals, or you could reach down and physically select it to off. If you touch the brake pedals, you do not have to outbrake its level. Keep in mind you cannot from RTO. This selector will stay in the RTO position. Auto brakes will be enunciated on the primary ICAS until you acknowledge it by turning the selector from RTO to off. At liftoff, the system says we are no longer needed, so the switch will physically trip from RTO to off, never giving you the auto brakes message on the primary ICAS. Auto brakes can be used for landing. We have 5 selections for landing, selections 1 through 4, and then max auto for a total of 5. All 5 positions compute a deceleration rate, and as a result will factor in reverse thrust. All 5 of these positions will bring you to a complete stop at the selected value, provided you do not disarm it. If auto brakes are no longer desired, you can disarm the system by again physically reaching down and selecting disarm, or the preferred method is to make a brake pedal application. You do not have to outbrake the level currently in use to disarm it. The selector will physically trip to the disarm position, giving you an auto brakes message on the primary ICAS until you acknowledge that message by turning the selector to off. If you land with this in any selection, example level 3, during the rollout you could increase to level 4, you could actually increase into level max, decide that's too much, and decrease. So after touchdown, you can increase and or decrease the auto brakes, provided you do not disarm it. Once you disarm the auto brake system, you're done. If the auto brakes are not armed at touchdown, please do not attempt to reach up and arm them. You can physically outbrake the max auto position. You cannot outbrake RTO. Auto brakes will work on a normal brake system, hydraulic system 4. Auto brakes do not know that the alternate brake system exists. Continuing the review, in the center of the overhead panel with our fire overheat test button. 3 areas of your airplane have both fire detection and protection capability. Sitting in a cockpit, 3 areas will tell you it's on fire and you can fight that fire. That would be the engines, APU, and lower cargo compartments forward and aft. 3 areas of your airplane have fire detection but no protection capability. That would be wheel well, wing overheat, and flight attendant crew rest area at door 5 right. 1 area of the airplane has protection but no detection. It would fight the fire, but you wouldn't know it was on fire. And that would be the lavatories. There's local detectors for the lavatories, but no indications on the flight deck. During the cockpit setup, the captain will do the fire and overheat test. All fire and overheat loops on the airplane are tested at this time. This is the only time 2 of those loops are ever tested. Those 2 loops would be the wheel well and wing overheats. A valid test on this would be when the primary ICAS indicates fire test pass. Moving to the right with the emergency exit lights, 3-position switch, off, armed, and on. The emergency exit light batteries will charge with this switch in all 3 positions provided DC bus 4 is powered. If you reach up and place the emergency exit light switch to on, the emergency exit lights will come on. The batteries will be powering the lights, and if DC bus 4 is still powered, it will continue to charge the batteries. However, the discharge rate is greater and the battery charge will deplete. Moving all the way over to the right is a fuel transfer main tanks 1 and 4 switch, primarily a maintenance switch. This switch, when pressed, opens transfer valves between main tanks. Pressing that switch allows gravity transfer between main tanks 4 into 3 and 1 into 2. Primarily a maintenance switch. Maintenance uses that switch to defuel your airplane to get the fuel out of the outboard main tanks. The only time the flight crews will ever use this switch is per an irregular procedure, such as 2 boost pumps in-op in an outboard main tank. Continuing the review with the fire control panel, which includes fire indications for the engines, the APU, and lower cargo, forward and aft. Please note that the APU fire control handle is a red light as the engines. Immediate action for engine fire, severe damage, or separation is to now call for the QRC for that condition. The immediate action for APU fire warning is again to call for the QRC for that condition. And immediate action for lower cargo fire warning is to now call for the QRC for that condition. Engines on the left wing, engines 1 and 2 on the left wing, share 2 bottles, bottle A and bottle B. If you discharge bottle A into one of these engines, bottle B can also go into that same engine, or it could be discharged into the other engine. There is no way to get these 2 bottles on this wing over to this wing. Likewise, there's no way to get the APU fire bottle to either wing. If you discharge one bottle into one engine, you can discharge the other bottle into the other engine by rotating the handle in the same direction. If you notice, the control handle shows left on engine 1, for example, is A, left on engine 2 is B. If you were to pigeon toe the fire handles, either toe in or toe out, that would discharge the same bottle. APU, only 1 bottle for the APU. Once that bottle is discharged to the APU, there are no other fire bottles available. Lower cargo, there are 4 bottles in that system referred to as bottles A, B, C, and D. Arming of a cargo fire button, either forward or aft, will accomplish 4 things, regardless of which switch you push. Arming either forward or aft will arm all 4 fire bottles, shut off all fans on the airplane. As a result of shutting off the equipment cooling fans with that group, equipment cooling will automatically go to override, as well as shut down pack number 3. In addition, arming the aft cargo button will also shut off aft cargo heat regardless of this switch position. In the event of a lower cargo fire, we call for the QRC. The QRC is going to have us arm the appropriate forward or aft button and then press the discharge. Please note it can take up to 30 seconds for the discharge light in the switch to illuminate, indicating that bottles A and B have discharged. Bottles A and B will give you an initial 30 minutes of protection. In 30 minutes, or landing, whichever occurs first, bottles C and D will then meter in over the next 2 hours and 30 minutes for a total protection time of 3 hours and 15 minutes. Dropping down to our ignition control panel, we have several selector switches here and start switches. Ignition, each engine has 2 igniters. There's a number 1 igniter and a number 2 igniter in each engine. We have the ability to select either or both igniters. Normal operations is to select a single igniter based on odd number flights or even number flights, and selecting both during irregular start procedures. Selecting the appropriate igniter, 4 things will activate that igniter and actually fire it. Turning on the continuous ignition switch, turning on the cell on the ice, flaps out of up, or a fuel lever out of cutoff with the N2 less than 50%. Any of the 4 conditions will fire this selected igniter. Standby ignition, normal SOP is to leave this switch in the normal position. In the unlikely event of a loss of all generators, the number 1 igniter on all 4 engines would fire using the backup power supply of DC. Reviewing now the engine start sequence and abnormal start procedures. Using the start switches on the overhead panel, engine start sequence is engine 4, 1, 2, 3. Once the engine is starting, the first officer will bring the fuel lever up to run when the N2 indicates 25% or max motoring, whichever occurs first, provided we're motoring above the minimum fuel on line. First officer brings the fuel lever up to run and hacks the clock. We have 20 seconds to have a light off indicated. Once the light off is indicated, we have to respect the 535 start EGT limit, which is indicated by the first red line. We must have an oil pressure indicated by 40% N2. We must have an N1 indicated by 40% N2. Once the first officer brings the fuel lever up to run, we have 2 minutes for the start EGT line to disappear, indicating that the engine is stable. If we encounter any one of those problems, electrical or pneumatic power interruption, immediate action for abnormal engine start is fuel lever to cut off and call for the QRC. Starters should disengage at 50% N2. If a starter fails to disengage, the ICAS message will give us a starter cutout message for that starter. The immediate action is to call for the QRC. To the right is our fuel jettison control panel. We have the jettison nozzle valves left and right, the jettison controller, and the fuel to remain. The jettison nozzles, the important thing to remember here is even if you're on the ground with the jettison selector to the off position, you can physically open the left and or right jettison nozzles. Not something you really want to do. Please keep in mind if maintenance is fueling your airplane, you would be defueling the airplane. The only time we should use these switches is in accordance with the fuel jettison procedure. Fuel jettison controllers A or B, we will select the desired system. When you do that, fuel temp on your lower right-hand corner of your primary ICAS is replaced with fuel to remain. That value can be increased and or decreased with the fuel to remain selector. There are 8 fuel tanks on your airplane, main tanks 1, 2, 3, and 4. 2 reserve tanks 2 and 3, which are physically outboard of your outboard main tanks. There's a very large center tank and a stabilizer tank. Of those 8 tanks, the only 4 tanks you can actually take the fuel out of and pump it directly overboard is the inboard mains, the center, and the stab. The stab does not transfer to the center. The stab dumps it directly overboard. To get rid of fuel during fuel jettison from the outboard mains, it would gravity feed to the inboard main, and the inboard main would dump it out. To get rid of fuel of your reserves, it again would transfer to the inboard main, and the inboard main would dump it out. So your wings transfer all the fuel to the wing root pumps it out. Fuel jettison selector. If in the process of dumping fuel the selected controller fails, the primary ICAS will indicate this. However, the other controller will automatically step in and continue to dump. Please remember that fuel jettison is not permitted while operating the flaps between positions 1 and 5 or 5 and 1. Our discussion of fuel management will begin with the airplane fully loaded with fuel, and we'll talk through the sequence of fuel management as it occurs during a normal phase of flight. With the standard fuel density, the maximum fuel weight on board the airplane is 3D8.7. We'll assume that the airplane is loaded to that value. During the initial captain's cockpit setup, the captain will set up the crossfeed valves on the fuel panel in accordance to the fuel load on board. Crossfeed valves 2 and 3 are always open regardless of fuel quantity. Whenever your total fuel on board is greater than 120,000 pounds, the captain will also open up crossfeed valves 1 and 4. Crossfeed valves 2 and 3 will always be open. Fuel loads greater than 120, crossfeed valves 1 and 4 will also be open. At this time, no boost pumps are turned on. Eventually, prior to pushback, the captain will turn on boost pumps in accordance with the fuel load on board. Regardless of fuel load on board, the captain will always turn on the main boost pumps in all 4 main tanks. If crossfeed valves 1 and 4 will open previously for fuel loads greater than 120, the override jettison pumps in tanks 2 and 3 will also be on. Bring up the fuel synoptic to verify whether the center wing tank and or the stabilizer tank contain fuel. If either of these tanks contain fuel, turn on the respective pumps for the center and or the stabilizer pumps. Note in this configuration that all boost pump switches are on. Not all pumps are actually running. The main pumps in tanks 1, 2, 3, and 4 are actually running, putting out pressure, as are the 2 center wing override jettison pumps. Note that the override pumps in tanks 2, 3, as well as the stabilizer tanks indicate on, but are actually not running. The overrides in tanks 2 and 3 and stabilizer are armed to come on at the appropriate point during fuel management. This can be verified by looking at the fuel synoptic on the lower ICAS. Note that the main pumps in tanks 1, 2, 3, and 4 indicate green, which indicates that they're putting out pressure, as well as the 2 center wing override jettison pumps. Note that the override pumps in tanks 2 and 3, as well as the stabilizer pumps, indicate blue, which indicates that these pumps are armed to come on at the appropriate time. Note that the fuel panel in this configuration allows the center wing override jettison pumps to feed all 4 engines for engine start and initial taxi. This is due to the higher output pressure of the center wing pumps over the main tank boost pumps. The next fuel system change to occurs automatically upon taxi out when the flaps are extended to a takeoff position. Whenever the aircraft is on the ground and the trailing edge flaps are set to position 10 or 20, crossfeed valves 2 and 3 will automatically close. As a result, the center wing override jettison pumps will continue to feed engines 1 and 4. However, the main tank boost pumps in tanks 2 and 3 will then feed their respective engine. This can be verified by bringing up the fuel synoptic. Note that the center wing tank override jettison pumps will continue to feed engines 1 and 4. However, the main boost pumps on tanks 2 and 3 will feed their respective engine due to the closure of crossfeed valves 2 and 3. Please note that the fuel panel indicates that the crossfeed valves 2 and 3 are still open. Whenever the trailing edge flaps are set to a takeoff position on the ground, these valves are truly closed. This can be verified, once again, by looking at the fuel synoptic. The next change occurs after airborne with the retraction of the flaps. Once the flaps are retracted, crossfeed valves 2 and 3 will reopen. As a result, the center wing override jettison pumps will return to feeding all 4 engines. This can be verified by bringing up the fuel synoptic, noting that crossfeed valves 2 and 3 have reopened, allowing the center wing tank to feed all 4 engines. The next fuel system change occurs automatically when the center wing tank volume reaches 80,000 pounds. The stabilizer pumps will automatically activate and transfer the fuel from the stabilizer to the center wing tank. This can be verified by bringing up the synoptic, noting that the center wing tank volume is 80,000 pounds. Note that the stabilizer pumps are now green, indicating the pumps are actually running, putting out pressure. Note the transfer arrow from the stabilizer tank to the center wing tank, indicating that stabilizer transfer is occurring. This will happen automatically, regardless of whether the fuel synoptic is displayed. The next fuel system change to occurs with a ICAS message of stab pump left and/or right. This would require the crew to bring up the fuel synoptic and verify that the stab is in fact approaching empty. With regards to stabilizer fuel, no crew action is required until both stab pump left and stab pump right messages are indicated. With both messages indicated, the synoptic for fuel will be verified that the tank is in fact empty. Whenever the flight crew changes fuel panel configuration, the other crew member should always be advised. Upon notifying the other flight crew member, stab pump left and stab pump right switches would be turned off. Note that during this time, the center wing tank was continuing to feed all 4 engines. The next fuel system change to occurs with an ICAS message of center wing override left and/or right message. With a center wing override left and/or right message displayed, the fuel synoptic is referred to. Center wing tank volume should indicate approximately 2,000 pounds. So with regards to the stabilizer, both the stab pump left and right messages are required before crew action. With regards to the center wing tank, either center wing override left or center wing override right message is required for crew action. Notify the other flight crew member that you are turning off both center wing override left and right boost pumps. At this time, the override jettison pumps in tanks 2 and tank 3 are now feeding all 4 engines. This can be verified by bringing up the fuel synoptic. Note that the override jettison pumps in tanks 2 and tank 3 have activated and are now feeding the engines on their respective side. The next fuel panel change to occurs automatically when the first inboard main tank 2 or main tank 3 reaches 40,000 pounds. First inboard main to 40,000 pounds will automatically transfer both reserve tanks to their respective main tank. This is a gravity transfer only. There are no transfer pumps associated with this system. This can be verified by once again bringing up the fuel synoptic, noting that reserve tanks 2 and 3 transfer arrows are indicated to the respective main tank. The next fuel system change to occurs with an ICAS message, fuel tank/engine. Note, as a ballpark, total fuel on board should be approximately 120,000 pounds. The change occurs with the ICAS message. With the ICAS message fuel tank/engine, the flight crew will bring up the fuel synoptic and verify that all 4 main tanks are in fact equal. The pilot making the change once again will notify the other flight crew member that we are returning to tank to engine. To do so, we turn off the overrides in tanks 2 and 3, as well as closing the crossfeed valves to 1 and 4. We are now burning tank to engine. Limitations has a minimum desired landing fuel value of 11,100 pounds. Fuel imbalance limits. Fuel imbalance limit between main tanks 1 and 4 is 3,000 pounds. Fuel imbalance limit between tanks 2 and 3 is 6,000 pounds. Whenever tank to engine configuration, the total of main tanks 2 and 3 must be within 6,000 pounds of the total of main tanks 1 and 4. This limitation only applies when burning tank to engine. Moving down below the fuel panel, you'll find the anti-ice control panel, which includes the controls for engine nacelle and wing anti-ice. The cell anti-ice uses pneumatic air to heat up the lip of the inlet. The EPR probe is heated electrically whenever the fuel lever is out of cutoff. The cell anti-ice is required anytime icing conditions exist, visibility of a mile or less, and the outside air temp is less than 10 degrees. Wing anti-ice, one switch for 2 valves, uses again pneumatic air from the pneumatic system to heat up the leading edge of the wing. The cell anti-ice is used as an anti-ice. Wing anti-ice is used as a de-ice. The book actually has you let the ice build up first before you turn it on. Wing anti-ice cannot be used on the ground, and it's not effective in flight whenever the flaps are extended. Window heat will turn on the window heat left and right. These switches control window heat to the number 1 windows only, L1 and R1, for strength and anti-ice purposes. Windows 2 and 3 are heated with low voltage only for defogging purposes whenever there's power on the airplane. Lower right-hand corner of the overhead panel is our pneumatic control panel. Engine bleed air switches are electrically controlled but pneumatically operated. So when the captain reaches up and turns these bleed air switches on, they're still going to stay off because it's going to take air off of the engine to physically open the valve. Please remember that with the APU running and the APU bleed air switch on, the APU bleed air is trying to force its way backwards through that valve. So at this time, that valve would be closed as a check valve, preventing that from happening. The only time airflow is ever allowed backwards through your engine bleed valve is during engine start. Sys fault lights for your pneumatic system will come on for one of 4 reasons: high system pressure, high system temperature, if the PRV valve is open when it's commanded closed, or if the HP valve is open when it's commanded closed. If a PRV or HP valve is open, that can result in high temp and or high pressure. It is not a valve disagreement light, because if those valves are closed when they're commanded open, you get ICAS messages, but you will not get the sys fault light, because in that condition, it cannot destroy the system. Continuing up, we have 3 air conditioning packs, number 1, a number 2, and a number 3 pack. All 3 packs put out the same temperature. That temperature is determined by the coldest zone. There's no sense having the packs work harder than what they need to. So the packs put out the temperature called for by your controlling zone, or coolest zone. All 3 packs put air into one manifold. So it's not which pack you turn on to cool the flight deck the best, it's the number of packs that increases the flow. Each pack has 2 controllers. There's an A controller and a B controller. The captain will reach up and select the normal position. The reason for this is because the system will use the opposite controller from what was used last flight. It alternates between the 2 controllers. To determine which controller is in use, bring up the ECS synoptic, and the controller in use will be indicated inside of the pack circle. If the selected controller fails, the other controller will automatically step in. If you are in a selected controller A or B and that controller fails, it again will use the other controller to step in. As far as pneumatically driven items and where they get their air source from, on the engine, prior to the bleed valve, there are 2 components on each engine that are pneumatically driven using pneumatic air from that engine. That would be the engine starter and the cell anti-ice. On the wing manifolds, between your engine bleed valves and your isolation valves, out here on your wing manifolds, the left wing manifold and the right wing manifold, there are several items on the wing manifolds. The air conditioning pack, the air demand pumps, wing anti-ice, and leading edge flaps. Also note that the hydraulic reservoir head pressure receives pneumatic air from the respective wing manifold. On the center manifold, here, probably the most important thing on the pneumatic center manifold as a flight crew member is the lower cargo fire detection system, aft cargo heat, with other items to include the number 2 pack, trim air, and potable water tank pressurization. Note, in the pack reset switch, we have a sys fault light which will illuminate if an air conditioning pack trips off due to a pack fault. Each pack has the ability to trip due to a pack fault. individual of each other. In addition to a pack fault, pressing a cargo fire arming button for the lower compartments forward or aft will shut down pack 3. In addition to a pack fault, overpressurization on your airplane will trip pack 2. Remember that your packs have two flow modes, high flow and normal flow. The packs operate in high flow until top of climb, which is determined by the FMC, at which point they will transition to the normal flow mode and will stay in normal flow until reaching the top of descent point, again computed by the FMC. So if a step climb was to occur between top of climb and top of descent, the packs would be in normal flow. If any pack for any reason shuts down, the remaining packs will instantly go to high flow. To determine a flow mode of your pack at the current time, bring up the ECS synoptic. Above the pack circle will be indicated high flow or nothing for normal flow. Continuing our discussion with equipment cooling. Equipment cooling draws cabin air into the E&E racks downstairs below the first class and discharges that equipment cooling air one of two places, back inside the lower cargo compartment or overboard, depending on the outside air temp. With the selector in normal, we're on the ground at the gate, engine shut down, outside air temp less than 45 degrees, the equipment cooling air will be discharged into the forward cargo compartment. Temperature greater than 45 degrees, it'll be discharged overboard. For temperatures greater than 45 degrees, with the equipment cooling air being discharged overboard, with that overboard valve open, it increases the workload on the pressurization to compensate for that valve being open. So when you start your second engine, the airplane thinks you're going to go fly, so as a result, it will reroute all of the equipment cooling air back inside, regardless of outside air temp, closing that port, allowing pressurization to be more efficient. Equipment cooling to the standby mode forces it back inside if that fails to happen. Equipment cooling to override shuts off the supply fans and exhaust fans, shuts off the supply and exhaust valves, and as a result, equipment cooling is dependent on differential pressure. If differential pressure is low, equipment cooling is low. The greater the differential pressure, the more efficient equipment cooling. High flow, if we press this selection, the packs are in high flow. Humidifier, the flight deck and flight deck crew rest areas only are humidified. No other sections of the airplane are humidified. The humidifier takes water from the potable water system to humidify those areas. The captain will select the humidifier to on during the cockpit setup. The humidifier will not activate until the FMC top of climb and will continue to run in 2 hours prior to the top of descent. If your top of descent is within 2 hours of top of climb, the humidifier will not activate. However, in order for the humidifier to shut down, it needs to know the top of descent point. Thus, if the approach is not installed, there is no top of descent point. The humidifier will run until it can calculate that point. Aft cargo heat uses hot pneumatic air from the center manifold to keep the aft cargo compartment at a desired temperature. Because of the aft cargo heat, all live animals will ride in the aft cargo compartment. The forward cargo compartment is heated electrically to about 40 degrees. Upper and lower recirc fans. The upper fans will always run as long as the switch is on. The lower fans will run when the packs are in normal flow, which should occur shortly after top of climb. Aircraft trim air uses hot air off the center manifold to mix with cool air leaving the packs to adjust compartment temperatures to selected levels. Turning off the trim air will cause all three air conditioning packs to put out a temperature that keeps the temperature of the compartment at an average of 75 degrees. Above the air conditioning control panel is your pressurization control panel. Landing altitude selection over in the lower left-hand corner. Landing altitude in automatic allows the origin and destination airports to determine landing altitude. Landing altitude in manual allows you to increase or decrease the landing altitude value. Outflow valves, left and right, should indicate full open, not close as indicated here, while on the ground in the automatic mode. If at any time a manual selection is used, Using the switch to the open or closed position as desired drives the selected valves open or closed. Whenever the option is selected to manual, the cabin limiter of 11,000 feet is bypassed. Auto selector for cabin altitude control in normal, again, allows the system to alternate between controllers on each subsequent flight, or allows you to select the appropriate A or B controller. Regardless of the switch position used, if the selected controller fails, the other controller will automatically step in. Immediate action for a pressurization problem, which will result in a cabin clearly going above 10,000 feet, is oxygen mask on 100%. Crew communications established. Call for the QRC. Above your pressurization control panel is your oxygen control panel. 3-position switch, norm, on, and reset. This is the only switch required to be safety during the cockpit setups. That would put it in a norm position. In a norm position, whenever the cabin altitude exceeds 14,000 feet, the passenger oxygen system automatically activates. Regardless of cabin altitude, if you reach up and select the system to on, the system will activate regardless of pressure altitude. To reset the system, you must be below 12,000 feet of cabin altitude. Momentarily hold the switch to reset. Yaw dampeners, upper and lower, in-op light in each switch. The first IRS fully aligned will stabilize both yaw dampeners, thus putting out both in-op lights. In addition to the cockpit indication of the APU fire warning, externally in the right body wheel well or right aft wheel well is a remote shutdown panel for the APU. This remote shutdown panel contains a stop button, a fire control handle, a continuous horn, and a red light. The horn will sound continuous and the light will illuminate during an APU fire warning and an APU fire test. If the APU is running and it catches fire, it should shut down automatically. It cannot fire the bottle automatically. If the APU is running and the captain does the fire overheat test, it will activate the continuous horn and illuminate the red light. However, it should not shut down the APU. Our review now will move to the glare shield, which encompasses the EFIS control panels for both the captain and first officer, ICAS control panel, and mode control panel. EFIS control panels allow the pilot to select what's displayed for the PFD and ND and change various modes. EFIS control panel was to fail, moving to the CDU. CDU menu page allows us at one right to select EFIS control panel to control those functions in the event that the real control panel was to fail. Specifically on the EFIS control panel, we have a decision height and MDA option. Decision heights or radio altitudes displayed in the lower right-hand corner of the attitude indicator. MDAs or MSL altitudes and are displayed in the upper right-hand corner of the attitude indicator. SOP is to select one or the other. Do not have both displayed. To change the display, specifically for decision height or MDA, select the mode in which you wish to deal with. The small knob on top, increase or decrease that value. To get rid of a decision height, select decision height, turn it counterclockwise to indicate something below 0. Will blank the radio altitude display. To get rid of a MDA, select MDA, turn the selector counterclockwise below a minus 100 feet to blank the MDA display. Meters button. Meters allows you to display the meters equivalent of your actual and target altitude. It does not replace it. Pushing the meters button again removes that display. To set the altimeter, again, you have the ability to select either inches of mercury or hectopascals and millibars. Select the appropriate display. Increase or decrease the value proportionally. Pushing the standard button will automatically default to 2992 inches with STD displayed, or 1013 millibars, again with STD displayed. Left and right VOR ADF displays allow you to turn on a display for the left ADF or left VOR, as well as the right ADF and right VOR. This turns the display on and off. It does not turn the radios on and off. Mode selector for approach, VOR, map, and plan mode. The center button turns it into an HSI display. Pushing the center button again turns the nav display into an expanded display. Range selects 10, 20, 40, 80, 160, 320, 640 with the traffic symbology for TCAS. Weather radar, this turns on the weather radar transmitter. So this is basically the weather radar on-off switch. Stations, waypoint, and airport. We'll turn on the stations, waypoint, and airports based on range, high altitude or low altitude. That is FMC generated. That would not be raw data. To actually pull up the raw data, select position, that would be raw data azimuth and DME to the station. Data simply turns on the time on the nav display at which you'll reach the certain points. ICAS control panel, the recall cancel button, allow you to recall and cancel the ICAS messages on the primary, warnings, cautions, advisories, and memos. Please remember when you can cancel only the amber messages, thus the caution and advisory. You cannot cancel warnings and memos. All other buttons allow you to choose the synoptics for the lower ICAS. If your ICAS control panel was to fail, again, you could go to the menu page of your CDU, line select to right, and control the ICAS through the CDU. On the mode control panel, flight director switches. Flight director switches allow you to turn the selected flight director on or off. Auto throttle switch, manually armed, must be manually disarmed. Unlike the classic 47, this switch is not electrically latched into position. Auto throttles have the ability to go after a thrust setting or a speed. The pitch mode of the airplane basically determines which mode of the auto throttles they should be in, thrust or speed. You can use auto throttles without the autopilot and flight director. Thus, you have to reach up and tell the auto throttles which mode you prefer them in, thrust or speed. Roll modes of your airplane. We have TOGA, LNAV, heading select, heading hold, localizer, rollout, and attitude. Pitch modes of your airplane, again TOGA, VNAV, flitch, vertical speed, glide slope, flare. Any one of them, pitch or roll, can be used at any one time. Selecting one will disengage the other. 3 autopilots, a left, a center, and a right. The left autopilot uses hydraulic system number 3. The left IRS and AC bus 3. The center autopilot uses hydraulic system number 1, the center IRS, and AC bus number 1. The right autopilot uses hydraulic system number 2, IRS right, and AC bus number 2. Again, the gauge left, center, or right is always 3, 1, 2. Underlined numbers with regards to autopilots. The minimum altitude to engage an autopilot after takeoff is 250 feet AGL. The SOP is to call for it around 800 feet. Minimum altitude to have a single autopilot engage for an ILS approach is 100 feet AGL. If you do not punch that autopilot off, that single autopilot can take you all the way down the ILS, all the way to the runway. It will not flare, and it will bank to track the localizer. So minimum altitude single autopilot ILS is 100 feet AGL. Minimum altitude single autopilot non-precision approach is 50 feet below the MDA. Minimum threshold crossing height for the auto land on the ILS approach is 42 feet. Our review now will center in front of the captain to include the captain's source selectors, captain's PFD, and ND. Source selectors, the important thing to remember here are these are display switches only. These will not change any aircraft systems. These switches determine what information is displayed on the PFD and ND. Specifically, the flight director. Notice that the captain switches are in a 12 o'clock position, which basically puts him on the left sources. 3 flight directors, left, the center, and the right. As a result, with the flight director switch turned on, the flight director displayed is the one selected through this switch, in this case the left. Please remember that a flight control computer can either give you a autopilot or a flight director. It cannot give you both. So if I was to engage the left autopilot after takeoff with the captain and the left flight director, the captain's left flight director will disappear. Navigation source selector. Again, the captain is typically in the left FMC. That determines which FMC gets to display the ND and some information on the PFD, such as airspeed and other items. If the left FMC was to fail, moving this per the procedure to the right would reattach this information to the right FMC. If the right FMC was to fail, we have the ability to select our information from the left CDU only or the center CDU. IRS, left, center, or right, as we discussed earlier, the fully aligned IRS will generate some items on the PFD, some additional information on the ND. That source of IRS information will come from the IRS selected. Air data computers, there's only a left and a right. Typically the captain is on the left air data to give you airspeed and altitude information. EIU selector, EIU, there are 3 EIUs, a left, a center, and a right. The 12 o'clock position puts the captain in auto. That allows the left EIU to generate the PFD and ND symbols. If the left was to fail with this switch in auto, it would automatically move over to the center EIU to generate those 2 pictures. We have the ability to select any of the 3 EIUs to paint the PFD and ND. Likewise, the source selectors for the first officer over on the right-hand side. Again, the 12 o'clock position, but then the information would be coming from the right sources. Right flight director, right FMC, right EIU, right IRS, and the right air data computer. Discussion now of the PFD. A vertical tape for airspeed. Your indicated airspeed is always indicated here in the center. Your target airspeed is always indicated in the top in magenta. Keep in mind your target airspeed can either be MCP or FMC driven. In either case, it will show up in magenta. To determine if it's MCP, you look at the MCP airspeed window. If the airspeed window is open, such as numbers displayed, that target airspeed is MCP driven. If the indicated airspeed window is closed, no numbers, the target airspeed is FMC driven. Turbulent air penetration speed is 290 or 0.82 Mach. Flight mode enunciations for auto throttle, roll, pitch, and autopilot flight director statuses. Altitude, MSL altitude in vertical tape. Your actual altitude is always displayed in the center of the tape, with your target altitude always displayed at the top. Again, your target is always magenta. This target altitude is always MCP. It's never FMC. Your altitude window on your mode control panel is always open. Vertical speed comes from the accelerometer of your IRS. Anytime you climb or descend in excess of 400 feet per minute, you pick up the descent or ascent rate specific. So anytime more than 400 feet up or down, you pick up the specific, in this case, descending at 850 feet a minute. We incorrectly have both the MDA and DH displayed at this time. That's non-SOP. It's one or the other. If this is a Category 3 approach, we have a DH set, which represents an alert height. If this is a Category 2 approach, we have a DH set, and it represents a decision height. If it's any other approach, it will be based off of MDA. MDA is an MSL altitude. As a result, you get the altitude bug at the equivalent point. Decision height is a radio altitude. There is no bug on the MSL tape with regards to decision height. Radio altimeter at the bottom of your attitude indicator, the white numbers will appear anytime your airplane is below 2,500 feet AGL. Descending below 1,000 feet, the runway symbol will appear around the radio altimeter. Descending below 200 feet, the whole package will rise to touch the bottom of the airplane symbol upon touchdown. The pitch limit indicators, or eyelashes or whiskers, represent the max pitch attitude of the airplane based on your current configuration. This is automatically displayed whenever your flaps are out of up. Maximum cruise altitude is 45,100. Okay. As far as autopilot flight director status is coming down final, regardless of the number of autopilots we have selected engaged on the mode control panel, this indication on the FMA tells us how many are engaged. Example, let's simulate that all 3 autopilots are selected on the mode control panel. However, this indication is FD, that's flight director, and then as a result, no autopilots are engaged. If this says CMD, 1 autopilot is engaged. And if you have a flight director displayed, you know it's not this autopilot. If it says land 2, there are at least 2 autopilots engaged. Land 2 does not require the electrical system to isolate. If this says land 3, all 3 autopilots are engaged and the electrical system is isolated. Electrical system did not isolate, this would not say land 3. Keep in mind, whenever the autopilot is shooting the approach, be it single autopilot or multiple autopilots, the autopilot will use the expanded localizer scale. This indication is incorrect in the fact that you've got your normal localizer scale, which is what you would see displayed if you were hand flying the ILS. Whenever the autopilot shoots the approach, it's the expanded localizer, so we should have 1 box to the right and 1 box to the left, which is the half scale or expanded. Moving to the right of the PFD, our nav display, or ND. Upper left-hand corner of the nav display, we always have our current ground speed displayed. Remember, there's 3 taxi speeds as we go out, or taxi in, that we need to respect. Ground speed, upper left-hand corner, recommended straight ahead speed is 25 knots. If you're making a turn less than 45 degrees, the recommended speed is 15 knots. And if the turn is greater than 45 degrees, 10 knots. In excess of 100 knots, we pick up true airspeed and wind information direction, and velocity with the direction arrow. Upper right-hand corner, regardless of the range you have displayed on the nav display, the active waypoint will always appear in the upper right-hand corner. The time at which the FMC computes you get into that active waypoint and how far away that point is. The route line on your nav display, it is possible to have 4 different route lines displayed. A solid magenta line is the active route, be it route 1 or route 2. A dashed white line is a modification to this active route. A dashed blue line would appear for the inactive route, and a dashed magenta line, not to be confused with this dashed magenta line that goes out to the heading bug. The other dashed magenta line is an offset. So if I was to insert an offset, it would offset this entire route and it appear as dash white because I'm modifying the active route. When I execute the offset, the dash white turns dash magenta. I still have the solid magenta. The airplane will turn to fly the offset. So again, solid magenta is active route. Dashed white is a modification to the active route. Dashed blue is an inactive route. Dashed magenta is an offset. Now this dashed magenta line here pointing out to the heading bug, it is possible because of the expanded display here to slew that heading bug off the scale, at which point this dashed magenta line would follow it all the way around and 10 seconds later disappear. VOR display. In this particular case, the left VOR is selected on the EFIS control panel. It says VOR left. I have the identifier and I have the DME. If it was tuned but not identified, it would say VOR left with the frequency. It would not show DME. If this information was blue, that would be in regards to the ADF. The ADF, it would say ADF left. It would show frequency until it was identified, and once it was identified, it would show identifier. There is no DME associated with an ADF. Likewise, over on the right, the same would be true for the right VOR or right ADF. Descent path indication, we have reached the top of descent point we have programmed in the FMC. As a result, we pick up our descent path indicator. Full scale, in this particular case, the magenta diamond is right on the path. If we were to deviate below, the diamond would start to rise to full scale. In excess of 400 feet up or down, you'll pick up how far above or below the path you are. IRS-3 GPS. Let's discuss now the big picture for the flight management computer system. We'll try to bring all the pieces into one big picture, talk about them individually as we go, and hopefully it'll come together. Flight management computer system. Start off with, let's talk about our IRSs. We've got 3 IRSs. An IRS left, we've got an IRS center, and we have an IRS right. Again, IRSs do not navigate. They're not built to do it. It's impossible for them to do it. So the component on your airplane that's responsible for navigation are your FMCs. We have a left FMC and a right FMC. FMCs are tasked with the navigation of the airplane. The nav display, lower right-hand corner of the nav display, IRS-3. Ideally, that's what we'd like to see. What that's telling you, IRS-3 specifically, is on that side. For the captain, it's the left. For the first officer, it's the right. All 3 IRSs are providing position information to that FMC. So the IRS, each one is receiving its signal, lat-long-wise, into that FMC. That FMC will take those 3 positions and average it. Comes up with an average position. At the same time, the right FMC is doing the same thing independent of the left. Again, it takes the 3 positions and averages it. The 2 FMCs then talk to each other and compare information. There are trigger values in there that if that information is too far off, it will resync the FMC and can generate some FMC messages on the ICAS if it gets out of limits. All right. Once the FMCs have computed the FMC position by averaging the 3 IRS positions, it will update that FMC position. Ideally, in order, it would like to use GPS. GPS follows us all over the world. So GPS is primarily going to be the update source. The FMC will get to determine what the update source is going to be. So what that's telling you is, in this case, GPS is the update source for your FMC's computed position. Likewise, the captain is doing the same thing. GPS is the update source. If GPS is not available, in the order of priority, if GPS is not available, it'll use another update source. DD for dual DME. Another source would be VD. If it only has 1 station, if it has 2 stations, it prefers dual DME with no azimuth. If it has a single station, it'll use azimuth and DME off of that station. Finally, towards the end of the flight, probably the only thing other than GPS you'll probably ever see is loc. Because coming down final, it might like the localizer reference a little better for update information. The thing is the FMC gets to choose which of those it gets to use. So this is what the nav display is showing you. IRS-3 for 3 position inputs to each individual FMC, computes the average position and updates it with its source. The question is, what happens if we're flying along and we lose an IRS? Let's say the left IRS fails. At that particular time, if the left IRS was to fail, the captain's, by the way, 3 is the only digit you'll ever see here. The captain's FMC will go looking, or the left FMC will go looking for the left IRS. But because the left IRS was the one that failed, it then tasks the center IRS to provide lat-long information to the left FMC. The right IRS is still tasked with position information to the right FMC. So now instead of 3 positions, now you only have 1 position. So now the FMC is using those positions. In this case, this is the right, and this is the center. As a result, the captain's nav display will say IRS center. The first officers would say IRS right. It will still show what the update source is to that position. But now it's showing you specifically which IRS is tasked with lat-long information to the respective FMC. Okay, continuing on with now all items functioning. In addition to the IRSs, we have CDUs. We have 3 CDUs. We got a left CDU, we have a center CDU, and we have a right CDU. Now, I'm placing them in front of the IRSs. The position isn't really relevant. It's just that it goes hand in hand. The parts are important for the big picture. The CDU, the primary purpose of the CDU is to allow the flight crew to communicate with the FMC. Your data input goes through the CDU. It also allows the FMC to communicate with you. FMC scratch pad messages like reset MCP or drag required. So it's a communications outlet between the CDU and the FMC. It allows you to communicate. Likewise, the right one is wired to the right. Now, the center CDU cannot do FMC work. It's impossible. The center CDU is connected to the left FMC. It communicates with the left MC with ACARS and SATCOM, but no FMC. So this signal flow is specific just to these few items. All right. Information in the FMC is going to be sent out to several locations. That FMC information is sent out to the nav display and the PFD. Likewise for the captain. PFD and nav display. So that's for our display purposes, but we need it to control the airplane as well. So down here, we have our airplane systems. We have EECs, electronic engine controls. We have FCCs, flight control computers, and we have our VHF nav radios. These two FMCs, again, share information, so if you put something into the left CDU, which stalls it in the left FMC, it appears in the right CDU through this signal flow. Like the pilot and the first officer, the captain and the first officer, both pilots are qualified to fly the airplane. So the left FMC is just as qualified as the right FMC to fly the airplane. But only one actually gets to control it. Which FMC will control my airplane systems? And that's through the FMC master selector on the center panel. Everything being normal, we typically, per SOP, select the left FMC, which gets to talk to my EECs, my flight control computers, and my nav radios. The reason for the left FMC and not alternating between left and right like we do on every other thing is because the left FMC has the backup power source. The right FMC does not have a backup power source. Specifically, electronic engine controls. What they're getting their signal from the FMC is the auto throttle function. What power to set, when to throttle back, when to push up climb power. I meant auto throttles. Flight control computers, specifically what they need is the LNAV and VNAV signal from the flight control computer. When to turn left, when to climb up. And when I climb, set climb power. The nav radios, what to automatically tune them to, auto tune. So if you don't have the nav radios manually tuned and you've got them in the FMCs able to tune them, the FMC will automatically tune it based on a route, a procedure, or automatically for updating purposes like we talked about. But the auto tune, the LNAV, VNAV, and the auto throttles get their signal from the selected FMC. Now, the picture here, if everything is running fine, let's say we're flying along and the left FMC was to fail. If the left FMC was to fail, the EECs would still work, but the auto throttles would not. So we'd get an auto throttles ICAS message because they don't know what power to set. The flight control computers would still work, but there's no LNAV and VNAV capability because they no longer know when to turn and when to climb. The auto-tuning of the nav radios are still going to work because the other FMC is still functioning. You have to lose both of them before the auto-tune feature goes away. In this particular case, we're going to get two ICAS messages. We're going to get FMC left, and we're going to get, well, actually we're going to get three. We're going to get auto throttles, FMC left. Those were the two messages we were going to get, auto throttles and FMC left. The procedure for this particular irregular has us move two switches. The first switch we're going to move is going to be the captain's nav source selector right here. Because with this in left, the left FMC is dead. So this CDU right now and this nav display is very limited in what it can show you. In fact, it has progress and legs available. Because in order for it to show anything else, it has to come out of this database, which is gone. So the first procedure will have us, the switch will have us move us to the right FMC for the captain's display. What that will do is that will rewire the CDU, the PFD and ND over to the right FMC. And as a result, the captain can get all of the information displayed back that the left FMC took away. The second switch we're going to move is this selector switch here. The procedure will have us move this to the right. And when we do that, we regain our signal flow to our auto throttles, to our LNAV and VNAV, and our auto tuning of the nav radios. Please note that if this FMC was to fail, it will not automatically switch your systems over. The irregular procedure has us doing it. Likewise, this will not automatically switch over. The irregular procedure has us moving that display switch. So then you're having a really bad day, and the right FMC decides to take a dump. So if both FMCs are dead, we're in standby navigation. In standby navigation, we have no auto throttles. They are now gone. The EECs still operate. The engine's going to run, it just won't know what power to set, so you have to manually set it. LNAV and VNAV are gone. It comes from the FMC, there's no way to do it. The flight control computers will still work, but you have to heading select yourself, or heading hold, or our altitude hold, or vertical speed, or flitch, but there's no LNAV and VNAV. The auto tuning of the nav radios are gone. The nav radios will still work, but you have to manually tune them. In fact, you will manually tune the left VOR, the left ADF, and the left ILS on the left CDU. You'll tune the right radios, VOR, ADF, and ILS on the right CDU. You need to go to the center CDU and tune the center ILS if you expect the center autopilot to fly the approach. Can you do a Category 2 approach in this case? Well, if we look at our mode control panel, the things we've lost auto throttle function, so the thrust and speed mode of the auto throttles are gone. We lost LNAV and VNAV. Everything else works. In fact, you're basically on a 747-100, a classic 47. You have everything you still need to shoot a Category 2 approach. You cannot do the Category 3 approach because you need the auto throttles per limitations. So in standby nav, we can still get a Category 2 approach out of it. Legs. All new waypoints have to be loaded as lat longs, because in order for it to put in a specific point, it has to go to the database to pull it out, which is gone. So all new waypoints have to be lat longs. You can heading select yourself to the new waypoint. The CDUs have the ability to hold up to 120 waypoints. So this is basically the big picture for the flight management computer system. Continuing a review of the center portion of the forward panel, our standby instruments, standby altimeter, standby airspeed indicator, and standby attitude. Brightness controls for the upper and lower ICAS. EIU selector, 3 EIUs. This EIU in the auto position allows the left EIU to generate the primary and secondary graphics on the primary and secondary ICAS. You have the ability to select any of the 3. Likewise, with this in auto, if the left EIU was to fail, the center EIU would pick up the primary and secondary ICAS. Heading select switch, whether it be true or magnetic heading. FMC master selector. This switch allows the left or right as selected FMC to control the EECs, FCCs, and auto tuning of the nav radios. We operate with the left FMC selected all of the time, because the left FMC has the backup power supply, the right FMC does not. Primary ICAS, pretty much the fixed format, generating EPR, N1, and EGT. Remember that the EECs will generate the EPR, the EGT, and the oil temp values for display. With the engine shut down, the EEC is not turning. There will be no EPR, no EGT, and no oil temperature values or pointers whatsoever. As soon as you start the engine, generate some N2 RPM, EPR, EGT, and oil temp will appear. Thrust mode enunciation, in this particular case, go around or GA is enunciated with the limiting EPR of 1.50. Various thrust modes we can encounter here is TO for max EPR, D-TO for reduced EPR, climb, climb 1, climb 2, continuous, cruise, go around. All of those are different thrust modes with the appropriate limit EPR displayed in green. ICAS messages, we have 4 messages we can display on our primary ICAS. A red message is a warning. An amber message is either a caution or an advisory. If it's indented one position, it's an advisory. And the white messages are memos. In this particular case, we have a warning, a caution, advisory, and a memo displayed. If I was to push the cancel button on my ICAS control panel, the 2 amber caution and advisories would disappear. The cancel button would not cancel warnings or memos. The landing gear indication, and in this particular case, a single indication because all 5 nose, body, and wing gear are down and locked. If a landing gear was to encounter a problem, this would automatically expand into the expanded display, showing each specific gear. Flap indication, we're in the primary drive, everything is working fine, so as a result we have this single vertical tape indication on the flaps. Total fuel value, standard fuel density, the maximum fuel weight you can cram in the airplane is 388.7 on the pounds. Fuel temperature is displayed, and if you have engines or ECS selected on the lower or secondary ICAS, you have ECS information as a result, showing duct pressure in both the left and right wing manifolds, the current cabin altitude, the landing altitude, the differential pressure, and the climb or descent rate. Landing gear. Landing gear is typically operated through the hydraulic system, System 1 and 4. System 1 again operates the nose and body gear. System 4 operates the wing gear. If the hydraulic system was to fail, you have the ability to alternately extend the nose and body gear and or the wing gear independent of each other. These switches simply rotate the up locks for the door and the gear, allowing those 2 items to gravity fall. These switches cannot pull the gear down and locked. The gear must be on the up lock in order for these switches to be of benefit. Also, if you extend the gear through the use of these switches, the landing gear doors will remain open. Moving down to the secondary or lower ICAS, in this particular picture we have the engine synoptic displayed. You have the ability on the ICAS control panel to bring up any of the synoptics. Engine synoptic here, we have the N2 RPM, we have the fuel flow indication, oil pressure, oil temperature, oil quantity, and the vibration meters. Notice that the oil pressure and oil temperature scales have an amber and red range. This line on number 3 engine, which is shut down, indicates the minimum fuel on line, which would disappear after the first officer brings the fuel lever up to run. Oil quantity, the minimum oil quantity for engine start is 18 quarts. Other synoptics again available would be fuel, hydraulics, ECS, gear, so forth. Continuing our review on the center aisle stand, moving further aft, our stab position indicator for both the captain and first officer. Remember, stabilizer trim is pressurized by hydraulic system 2 or 3. One of those 2 systems must be pressurized in order to move the stabilizer. The airplane has the ability to expand a normal green band range forward or aft for airplane nose down and airplane nose up based on the amount of weight on the nose wheel and the value of the CG you type in on the takeoff page. Speed brakes. Speed brake lever in flight cannot go beyond the flight detent. It's physically impossible to bring it beyond that point. There is a lever lock there that prevents that operation from occurring. On the ground, the lever lock is removed so the speed brake handle can be pulled all the way to the up position. Unlike the classic 47, you can use speed brakes in flight with flaps extended on the 400, not recommended beyond a trailing edge flaps of 10. Speed brakes for arm, pulling this handle up and slightly aft will arm the speed brakes for deployment. Two conditions have to be met in order for the speed brakes to deploy. Main wheels must be on the ground or untilted, and the throttles must be at idle. Those two conditions are met, the speed brake handle will deploy all the way to the up position. If you forget to arm the speed brakes for landing or reject a takeoff, with the throttles closed, going into reverse thrust will arm them, and because you've met the other conditions, as the main wheel's on the ground and the throttle's closed, the speed brakes just continue all the way to up. Unscheduled stabilizer trim. The immediate action for unscheduled stabilizer trim is to oppose the trim and call for the QRC for that condition. Stab trim cutout switches, one for system 2, one for system 3, is a 3-position switch. If I lift the guard, the switch in the aft position is cut out. The vertical position is auto, the forward position is on. The difference between auto and on. In the automatic position, the stabilizer trim, when it detects movement, will look for an input signal from an autopilot, from a yoke switch, or from the alternate switch. If it does not find an input signal, it will automatically shut off all hydraulic fluid to the stabilizer. If the switch was in the on position and the stab moved, the system does not look for an input signal, and thus an unscheduled trim is allowed to continue. Alternate stab trim switches. These switches simply are different wiring back to the control module. You must have hydraulic system 2 or 3 pressurized or the stab will not move. If you use these alternate trim switches, you can get a greater range of trim over the yoke switches. Use of the alternate trim switches will also not disengage an autopilot. If you use a yoke switch, it will disengage the autopilot. Evacuation control panel, left aft end of the center aisle stand. Immediate action for evacuation is ATC notify. Call for the QRC. There are numerous switches throughout the airplane, flight attendants' positions at the doors, upper deck as well. Any one switch anywhere on the airplane will activate every light and every horn on every panel. Pressing the button on that panel will silence the horn on that panel only. The light continues to flash until all control switches are returned to normal. Chalk talk with regards to flap control on our 400. Airplane has 3 modes of operation for flaps: primary, secondary, and alternate. Flap handle. Whenever the flap handle works, the 3 flap control units on your airplane are part of the operation. The 3 flap control units provide asymmetry protection and load relief. Asymmetry protection is on the leading edge and trailing edge flaps. Load relief is available just on the trailing edge flaps. Load relief. When you select flaps 30, and if you overspeed flaps 30, the trailing edge flaps will blow up to position 25. If you select flaps 25 and you overspeed them at 25, the trailing edge flaps will load relief to 20. So 30 to 25 and 25 to 20 is 4-0 load relief. If you overspeed them at flaps 20, they deplane. As far as the operations go, leading edge flaps, again, were pneumatic operation. Trailing edge flaps were hydraulic operations, systems 1 and 4. The flap handle on the primary drive obviously works. That's how we operate them all the time. The range on the primary drive, you can select anything from up to 30 degrees. When you go from flaps up to 1, you get leading edge, inboard, and mid-span. There are no trailing edge flaps at flaps position 1. It's all leading edge, well, partial leading edge. The inboard and mid-span come out. When you go from 1 to 5, the outboard leading edge flaps come out and trailers go to 5. Flaps 5 to 30 is trailing edge flaps only. Your display in the primary drive is a single vertical tape. Going into reverse thrust will retract inboard and mid-span leading edge flaps. So going into reverse thrust will automatically retract the inboard and mid-span leading edge flaps. As you come out of reverse, there's a short delay and those leading edge flaps will redeploy. So asymmetry protection, both leading and trailing edge flaps, load relief on the trailers only. and that's a function of the 3 flap control units to provide those 2 protective features. Leading edge flaps are pneumatically operated, trailing edge flaps are hydraulically operated. The flap panel does work. You can select anything from 0 to 30. Flaps up to 1, inboard and midspan leaders only. Flaps 5 to 1 or back either way. Outboard leading edge flaps and flaps to 5. Flaps 5 or greater is just trailing edge flaps only. Going into reverse thrust, leading edge, inboard, and midspan will retract. Single vertical tape display. Secondary mode of flap operations happens automatically. If you encounter a problem with the leading edge pneumatic or trailing edge hydraulic flap drives, the secondary function will automatically kick in. The 3 flap control units still work. You do have asymmetry protection on the leaders and the trailers in the secondary mode. However, you do not have load relief. Because the source of power to operate the trailing edge flaps in the secondary mode is electric motors. So by the time that electric motor was able to retract the trailing edge flap due to load relief, it would probably already be gone. So you lose that protection in the secondary mode. Likewise, the source of power to operate the leaders in the secondary mode is electric motors as well. Each group has their own motor. Those motors are different than the trailing edge motors. So an example here of trailing edge flaps, the outboard trailing edge flaps were to fail hydraulically. That means system 4 failed. The outboard trailing edge flaps would come out electrically. The inboard trailing edge flaps would continue on hydraulically through system 1. So just the affected set would deploy electrically. Leading edge flaps. If the leading edge flap on the, let's just draw an example here. Let's say we have our left and right wing. These are not to scale, by the way. You've got the inboard segments, the midspan segment, and the outboard segments. If I was to encounter a problem with the right midspan leading edge flap, the asymmetry protection would deploy the midspan electrically on the right wing and the left wing. So the asymmetry protection will drive out both sides electrically. Everything else will continue pneumatically. Now, I need to get rid of that. All right, so we continue on. Electric motors, the flap panel still works in the secondary mode. The range that you can select is all the way 0 through 30. Again, inboard leading edge and midspan leading edge deploy when you go from flaps up to 1. Out when you go from 1 to 5 or back, again the outboard leading edge and flaps to 5. 5 to 30, just the trailing edge. Your display in the secondary mode is expanded. You have an expanded display. You have 4 vertical tapes for your trailing edge flap segments and 6 leading edge boxes for your leading edge segments. Again, going into reverse thrust will retract the inboard and leading edge inboard and midspan leading edge flaps in the secondary mode. Basically, the only difference between primary and secondary is the amount of time to operate the affected set of flaps, because electric motors are a lot slower, the display, and no load relief. It's the only difference between primary and secondary. Alternate mode, on the other hand, is a different story. When you press the alternate flap arming switch, that will shut off the 3 flap control units, and as a result you have no asymmetry and no load relief. There are no flap control units. You shut them off, and that protective feature comes from those 3 flap control units. You're still using electric motors to drive out the leading edge and trailing edge flaps. However, it's different wiring. So it's a different control wiring out to the electric motor. So if your electric motor is giving you problems, you're not going to be able to deploy the affected flaps in either the secondary or alternate mode, but then the primary should have drove it out fine. If it's a control mechanism, then the electric motor should work, because we're going to use different wiring in either case. It's going to be different wiring with the same motor. The flap panel does not work in the alternate mode. So if I arm that secondary or that alternate flap arming switch, the flap panel is dead. You can move it all around, nothing's going to happen. What range can you select on the alternate mode? You can go from 0 to 25. There is no position 1 or 30 on alternate trailing edge flaps. Because when you take the arming switch to arm and then take your switch to extend, all the leaders and all the trailers come out at the same time. So there's nowhere to get partial leaders. Also, the flaps will automatically stop at 25, so there's no way to get to flaps 30. The display is an expanded display with tick marks, because you need to know when to take that alternate flap extend switch to off when you get to the appropriate 10 or 20 position. So it's an expanded display, but it has tick marks on it, and going into reverse thrust is not going to affect leading edge flap operation.